Hello and welcome to another NGen Math 6 lesson by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit 10, Lesson 4 on modeling with volume and surface area. Basically in this final lesson in this unit, we want to get more practice with volume and surface area of prisms and to a certain extent pyramids, right? We want to think about how these things play out. We want to look at some formulas for volume and surface area. We want to get fractions involved. We want to do a bunch of stuff, but mostly it's practice with volume and surface area. Now I'll be honest with you, some of the calculations that we do in today's lesson get lengthy. They might require a lot of space, especially if you're one, like me, that writes large. So I would suggest, as well as having our lesson worksheet sitting in front of you, you also have an additional piece of scrap paper that you maybe even would end up stapling onto the lesson itself, right? Just places where you can do some multiplication and some addition and things like that that you're going to need to do when calculating both volume and surface area. Anyhow, let's get right into it with the first exercise. Here we go. Volume and surface area are often used in real-world scenarios. I mean, all the time in the real world, we have to calculate both of these two quantities. Being able to understand which quantity, though, you should use in any particular situation is really important. Let's take a look at exercise number 1 to begin. A box is in the shape of a right rectangular prism made from cardboard that has dimensions of 18 inches by 12 inches by 8 inches as shown in the diagram. Letter A, find the volume of the box, show your calculations, and use appropriate units. All right, now we've certainly done volumes of boxes before, so what I'd like you to do is pause the video now and find the volume of this box, state not only the numerical answer, but make sure to include the appropriate units. All right, well, the volume of a right rectangular prism is its length times its width times its height. Now, multiplication is both commutative and associative, so you can do this product in any order that you want. You know, specifically, I'm going to have 18 times 12 times 8. If you're most comfortable doing 12 times 8 first and then multiplying by 18, or doing 18 times 8 first and whatever, you can do that. I'm going to literally take it in the order that it's in, and I'm going to first do my 18 times 12. This is where, again, it's really nice to have some scrap paper. All right. All right, and I find that, at least initially, I get that 216. By the way, remember that 216 actually represents the area of the base, right? 18 inches times 12 inches would be 216 square inches. Now what I'm going to do is I'm going to multiply it by the height, right? So 8 times 6 is 48, 8 times 1 is 8, plus 4 is 12, 8 times 2 is 16, plus 1 is 17. So my final volume is 1,728 cubic inches. All right. Now, volume is relatively easy of a right rectangular prism because we tend to have to do two products, right? The first product is the length times the width. We get that area of our base. Then we multiply the area of the base by the height, right? And we get the volume, 1,728 cubic inches. All right, and again, you can either write it like that or you can literally write it like this, C-U-I-N. Both of these are fine. You may want to check with your teacher which one she or he prefers. Now, let's take a look at letter B. All right. Letter B, draw a net for the object below, label all relevant dimensions. All right, so I want to draw a net for this object, okay? And nets all by themselves can be a little bit tricky. I'm going to pull my solid down here real quick just so that we can see it as we draw our net. Well, I already had the net there. There is my solid. Never mind. Let me put this thing back up here. Forethought. Here we go. All right, so I've already got my solid down here. Let's talk about drawing the net, okay? Now, remember, a right rectangular prism has 6 faces, 6 rectangles, okay? One of the nice things though is that really what you're gonna have is 3 pairs of identical rectangles. Now the bottom rectangle, the base rectangle, is gonna be 18 inches by 12 inches, and that's how I'm gonna actually start, okay? I'm gonna start with my 18 by 12 inch rectangle, okay? Now what I like to do is I like to think about folding down this side and folding down that side. Now when I do that, what's gonna happen is I'm gonna get these 2 identical rectangles, even if I don't draw them identical, and they're gonna both have that height of 8 inches. Remember, all I've done is taken this side and kind of folded it down, and this side and folded it down. I haven't folded the front down nor the back down yet. Maybe I'll do that right now. In fact, if I fold the front down, right, it's gonna go something like this, with this also being 8, and this also being, whoops, that's 18, but this is 8. Since I've got the 8s there, we'll just kind of leave it like that. Now, keep in mind, right now what I've got is I've got 5, right? The base, the front, the back, and the 2 sides, if you will. What I don't have is the top yet. Now the top is identical to the bottom base, so it's rather large, comes out like this, and it's 18 by 12. So there is my surface net, right? 2 bases that are identical, 18 by 12, right? The sides that are identical, 8 by 12s, and then the front and the back, 8 by 18. Okay? Now for letter C, the big one. Find the amount of cardboard that is needed to make the box in square inches. All right. Now, if you're wondering, oh, well, what are they asking for here? All you have to do is look at that. Square inches. In other words, I want the surface area. Okay, and this is going to take a lot of calculations because I've got 6 areas I've got to add up. Now, what I can do is calculate 3 areas and double them because every one of these things gets doubled up. Let's do the big one first, right? The big one is this 18 by 12. Now, we kind of already did that one, right? We did the 18 by 12 right up here when we found the area of the base up here. Right? But let me kind of number these. Let me call this 1 and 2. Let me call this 3 and 4. Let me call this 5 and 6. So, the area of 1 and the area of 2 is going to be that 18 times 12. And we did already do that up above, so I'm going to save a little bit of time here. That's going to be 216. Now we've got 2 of them, so let me write both of them right away, all right? I don't want to write just down one of the 216s and forget about the other one, right? Because I have 216 square inches inside of rectangle 1 and 216 square inches inside of rectangle 2. And again, I got that from just doing that product up here. Now let's do some of the other ones, okay? Why don't we take care of the rectangle 3 and 4, right? So the one up here and the one down here. Now those are ones that are 8 by 18. So we've got to do that somewhere. Let's do 18 times 8, right? That's going to be 64 and then 144. All right, so my area of rectangle 3 and my area of rectangle 4 are both going to be 144. All right. And finally, I've got 5 and 6, right? And 5 and 6 are these little rectangles that are 8 inches this way and 12 inches this way. So maybe I'll do that over here, right? And what we find is that 8 times 12 is 96. And we've got 2 of them. So those are area 5 and area 6, and they're both 96. And of course, now what I have to do, without a calculator, is I've got to add up all of these. But again, before we even do the addition, let's just make sure we understand what's going on here. Right, the 2 216s, those really come from the top and the bottom, the bases of my box, right? The 144s, those come from these sides that are 8 inches tall and 18 inches wide. And then our 296s come from the faces that are 8 inches tall and 12 inches wide. Now we just have to add them all up. Let's see if I can do it without making a mistake. So I've got 6 plus 6, which is 12, plus 4, which is 16, plus another 4, which is 20, plus 6, 26, plus another 6 is 32. All right, let me not lose my carrying the 3. I've got 9 and 9, which is 18, plus 4 is 22, plus 4 is 26, plus 1 is 27, plus 1 is 28, plus 3 is 31. And finally, in my hundreds column, 1 plus 1 is 2, plus 2 is 4, plus 2 is 6, plus 3 is 9. So I'm going to get 912. What are my units? Inches. So in this case, square inches. 912 square inches. All right, a lot of work for surface area. We actually have to calculate 6 different areas of any right rectangular prism. They're the simplest of things, right? They're boxes. But we still have to calculate 6 different areas. Granted, you know, these are the same, these are the same, these are the same, and then we have to add them all up super duper carefully. This is where if you do have a calculator, you know, on a phone or just a normal calculator, and you can check your work, you should do it by hand, but if you can then check your work on the calculator, it's awfully helpful. All right, let's keep going. Little volume and surface area. Now sometimes we're actually given a formula. Here it is, here's a formula to calculate either surface area or volume. And it's best if we actually understand the formula as well as just being able to like throw numbers into it, plug numbers into the formula. So let's take a look at exercise number 2. Consider the cube shown at the right. All the side lengths of the cube have been marked with the variable s. Letter A, the formula for the surface area of a cube is given by SA equals 6 times s to the second power. Explain where this equation comes from. All right, so I claim that if we know the length of the edge of a cube, and we call it s for side length, right? And that's really the side length of a square, right? So if s is that side length, then the surface area I'm claiming is 6 times s squared. I'd like you to pause the video now and see if you can explain where that formula comes from. Well, let's think about this for a second, right? All surface area is the sum of the areas of all the faces that enclose the solid. For a cube, we have 6 faces, and there's a 6 in our formula. They're all identical, and they're all squares. And in fact, they're all squares, right, that look like this. S and S. So the area of the square is equal to s times s, or s to the second, sometimes referred to as s squared, right? And then there are 6 of them. 6 identical squares so the surface area is 6 times s squared. So s raised to the second power simply is the area of one of the square faces. Multiply by 6 because you have 6 of them, and you've got the surface area. Now let's see if we can use this formula in a more challenging way. Letter B. Using the formula above, find the surface area of a cube whose sides are all 2/3 inches. Ooh, fractions, right? All right, but let's at least get it started together, right? We're told that the surface area of a cube is 6 times s squared. So in this case, right, we've got 6 times 2/3 to the second power. What I'd like you to do right now is pause the video now and see if you can figure out what the value of this is, and even though the directions don't say it, please state the value in the simplest form as a mixed number if needed. Pause the video now and see what you get. All right, well, let's kind of work it out. So we want to do 6 times 2/3 times 2/3. And if it makes you more comfortable to multiply everything so that it looks like a fraction, why don't we put the 6 as 6 over 1, or 6 divided by 1. Now we can do a little bit of cross-canceling here, not much, but we can do a little bit. We can say this 3 goes into this 6 2 times, right? Now we can do 2 times 2, which is 4, times another 2, which is 8. All right. Then in the denominator, we have 1 times 1, which is 1. 1 times 3 is 3. So in improper form, the answer is 8/3. If I want to change that to a mixed number form, of course, 3 goes into 8 2 times, with a remainder of 2. So the answer would be 2 2/3 square inches. 2 2/3 square inches. All right. So we should be able to do surface areas when the side lengths are fractional. All right. Even though it can turn out a bit uglier, we still can find that calculation. All right, let's keep going. Take a look at another problem. Actually, our last problem, but it's lengthy. Let's take a look at exercise number 3. 2 boxes used to hold sugar are shown below. One is a cube with side lengths that are 8 centimeters each. The other is a right rectangular prism box that is 16 centimeters by 4 centimeters by 8 centimeters. Letter A. Which box, if either, would hold more sugar? Show how you determined your answer. All right. Well, you've got 2 things to play around with here: the volume and the surface area of the boxes. The question is, which one of them is going to dictate how much sugar the box can hold? Why don't you pause the video now and see which of these boxes, if either, would hold more sugar. Pause the video. Well, to begin with, I hope that you realize that it's all about volume. How much something holds is all about the volume of that object. It's not about the surface area of the object. That has nothing to do with how much something can hold. You can actually have an object that has a very large surface area, but a very, very small volume. That can happen all the time. Doesn't happen a lot, but it can happen. All right, so I need the volume, right? That's what I need to determine which one of these will hold more. So the volume for at least the first object, so I'll put a volume with a little 1 there, is going to be base or length times width times height. All right, so obviously 8 times 8 is 64. Now I need to multiply by 8 again, so maybe I'll put the 8 down here to make it a little bit easier for myself. All right, and 8 times 4 is 32. 8 times 6 is 48, and then plus 3 is 51. So the volume of the first box is 512 cubic centimeters. All right, now let's figure out the volume of box 2. Whichever has the bigger volume is going to hold more sugar. So the volume of box 2 is going to be 16 times 4 times 8. All right, so 16 times 4 is 64. And then times 8 is going to be 512 cubic centimeters. And so the answer is that they both hold the same, right? And they both hold the same because they have the same volume. They both will hold the same. Have you ever seen a sugar cube? Right? There's not a lot of sugar cubes that kind of bounce around these days, but if you've been to a diner and watched your parents drink coffee or something like that, then you may have seen a sugar cube before. You may have even eaten one yourself. Those are about a cubic centimeter, a sugar cube. So we could easily see 512 of those sugar cubes fitting into both of these 2 boxes, right? They hold the same amount. They have the same volume. Now, just because 2 boxes have the same volume doesn't mean they'll have the same surface area. So let's take a look at letter B. The boxes will be closed on all sides by pieces of wood. If the wood is painted, which box will require more paint? Explain how you decided. All right, so now I'd like you to think about this. Which of these 2 boxes would require more paint to paint the entire surface of the box? Pause the video now and see if you can figure this one out. All right, well, this is all about surface area because we don't paint volume, we paint area, right? We paint flat surfaces. So let's figure out the surface area of both of them. All right, now the first one is a cube, right, that measures 8 by 8 by 8. So its surface area is actually pretty easy. We need to just simply find the area of one of the squares, one of the square faces, right? And that's 8 times 8, or 64 square centimeters. And then we need to multiply that by 6 because there's 6 of them. All right. So for the cube, we have 384. Let me write that a little bit neater. We have 384 square centimeters. All right. What we now have to do is figure out the surface area of this box, 16 by 4 by 8. So let me kind of get that one down here as well so that we can see it, hopefully. Just make sure that's not the best representation of it, but it'll get the job done. Now, right, we've got 6 of these faces just like we had 6 here. The unfortunate thing is that they're not all the same size, all right? But let's go with the bottom and the top first, right? The bottom and the top both have dimensions of 4 by 16. So the bottom and the top are 4 times 16, or 64 square centimeters, and there's 2 of them. Okay, so this is the bottom and the top, right? Right, now let's talk about maybe the front and the back, right? The front and the back are 16 by 8, right? 16 by 8. So if I have 16 times 8, right, let me kind of come over here, get some spare paper. 6 times 8 is 48, carry the 4, 12. So that's going to be 128 square centimeters, and there's going to be 2 of those. All right. Now finally, maybe the easiest one of all will be sort of this side, or sort of this face, and then the equivalent one that we can't see, and that's because it's got a 4 by 8 height. So 4 by 8 gives me 32 and another 32. So now, again, got to add them all up. Let's do it. Let's see if I can do it without making a mistake. I've got 2 plus 2 is 4, plus 8 is 12, plus another 8 is 20, plus 4 is 24, plus another 4 is 28. All right. Carry the 2, bring it up there. Hopefully I won't forget about it. I've got 3 and 3, that's 6, plus another 2 is 8, plus another 2 is 10, plus 6 is 16, plus 6 is 22, plus that 2 that I carried was 24. Carry the 2. And now I have 448. All right, and that's its surface area. So we don't have a lot of room to write our conclusion, right? What was the question? The question was which one will require more paint? And the answer is box number 2, right? So which would require more paint? Explain how you decided. We'll just put it right up here. We're going to say box number 2 because it has more surface area. All right, and painting is a really good example. When you paint a surface, right, it's a great example of where area is important, but volume is not. Now, on the other hand, if I was pouring paint inside of a box in order to fill the box completely up, that then would be an issue of volume. But if all I'm doing is just painting the outside of this box, then the one that's got 448 square centimeters of area is going to take more paint than the one that has 384 square centimeters. All right, let's take a look at one last one. Letter C. A third box is designed so that it is also a cube that has sides that are half of solid 1s. Find the volume of solid 3, then find the ratio of the volume of solid 1 to the volume of solid 3. Explain why the ratio isn't 2 to 1. All right, so a very simple idea, right? I mean, we've got this first one from up above, 8 centimeters by 8 centimeters by 8 centimeters. And then I create a new box where all of the side lengths are half of it. So instead of 8, 8, and 8, it's 4, 4, and 4. All right, what I want you to do is I want you to find the volume of this, then I want you to find the ratio of this volume to this volume, and then I want you to think for a minute about why that ratio, spoiler alert, doesn't turn out to be 2 to 1. All right, pause the video now and play around a little with this problem. All right, well first, let's figure out the volume of 3. So the volume of 3 is going to be 4 times 4 times 4. That's going to be 16 times 4, and that's going to be 64 cubic centimeters. Now, I want the ratio of solid 1 to solid 3. Now solid 1, let's go back up there, had a volume of 512, so 512 cubic centimeters to 64 cubic centimeters. That's my ratio. Now remember, a fraction is just a division problem. Okay, that's all it is. It's a division problem. And if you actually come over here and you do 512 divided by 64, what you'll find out is that the answer there is 8. You know, and you can check me on it here. I'll even do it myself, right? 8 times 6, 48. Another one, 512, subtract 0. Right, so the ratio is 8, or better yet, 8 to 1. Not 2 to 1, 8 to 1. And you might expect that, like, if I double all the side lengths of a cube, the volume should double as well, but it doesn't. It doesn't double, it doesn't quadruple. It increases by 8 times the amount. Why is that? Why is the ratio not 2 to 1? Well, it's not as simple or as obvious as one might think, because again, you would think, oh, I double everything, the volume should double. And yet that doesn't happen. And it doesn't happen because each of the 3 dimensions in length times width times height is doubled. So you really get 2 times 2 times 2, which is then 8 times as large. If we only doubled the width, but not the height and the length, or if we only doubled the height, but not the length and the width, then the volume would double. But because we've doubled each one of them, then in this calculation, length times width times height, since we've doubled, doubled, and doubled, each one of those doubling kind of compounds on each other, and you get a volume that's 8 times as large. We saw this the other day when we looked at a cube that had side lengths that were 1/2 centimeter each, or 1/2 inch each, and we saw that 8 of them then fit into a cube that had double those side lengths. Same idea here. All right, let's wrap this thing up. So today, we really didn't do anything new, right? We looked at surface area, and we looked at volume, and we worked only with right rectangular prisms, i.e. boxes, right? Surface area, strangely enough, turns out to be the one that's way more difficult to calculate, because you got to calculate a bunch of areas, sometimes up to 6 of them, and then add them all together, versus volume, where you're just multiplying 3 numbers together to get an answer. But of course, volume and area tell us very different things, or I should say volume and surface area tell us very different things. Volume, of course, tells us how much 3-dimensional space lies inside of an object, which then tells us how much that object holds. Surface area, on the other hand, tells us how much 2-dimensional space surrounds a 3-dimensional object and gets wrapped up into problems like what we saw with the painting. You know, which one's going to require more paint? Ah, the one with the greater surface area. All right. It's important that when you look at any kind of real-world problem that you understand whether or not you're working with volume or working with surface area. All right, for now, I just want to thank you for joining me for another NGen Math 6 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.